Welcome again, everyone, to our second keynote presentation from Dr. Russ Humphreys. Dr. Humphreys has a PhD in physics from LSU. After graduation, he worked at General Electric Corporation for a number of years. And after that, Dr. Humphreys worked at Sandia National Laboratories in New Mexico. He is well known. I probably don't need to introduce him to too many of you as a researcher, writer, and speaker of all kinds of creationary topics and events. He has been involved with a number of different creation organizations, working, writing, and speaking for them. The one that I'll mention is he is a longtime member and was a longtime board member of the Creation Research Society. Russ was also designated a fellow of the Creation Research Society because of his huge contribution to the cause of creation. I discovered that Russ enjoys hiking, and a couple days ago he was taken off on a hike and he had this big furry object on his back, and I said, "What, Russ, what is that?" He says, "Oh, I'm taking my pet yogi hiking." And I had this quizzical look, and Russ said, "I hope you can bear with me on this one." That didn't work. Anyway, see, it's Yogi Bear. Anyway, I was concerned. I said, "Russ, is this safe?" And he says, "Oh, it's quite safe because you see, Yogi, he has no teeth. He's a gummy bear." Okay, that's as much time as I'm going to take up. So without further ado, I'm going to stop my screen sharing. I'm going to disappear myself and turn it over to you, Russ.
Okay, I need to get my magic PowerPoint going. And let's see. Yes, it actually works. I'm always amazed that electronics works. Let's see if I can drag this thing out of the way. Okay. Okay. God's big magnets in the sky. I'm going to take you on a tour through the solar system, looking at the magnetic fields of the Earth, Moon, Sun, planets, and go out to the stars. First, let's look at how God made those magnetic fields. God used water to make the magnetic fields in the cosmos. A magnetic field, for some of you, reminder, is the invisible force that makes a compass needle point north. It has nothing to do with gravity, and nothing really to do with the spin of the Earth. So also, there's this. I'll get to how I used water in a moment. It explains the magnetic fields of planets, stars, and galaxies, clusters of stars, big clusters of stars. So how, you're wondering, how can water make magnetic fields? Well, water has hydrogen atoms in the molecule, and the nuclei of hydrogen atoms have magnetic fields. In fact, any spinning electric charge makes a magnetic field. Any moving electronic charge makes a magnetic field. Now, electrons have big fields, and the electrons, if you can see my cursor, if I can get it over here, yes, the big blue circle there is the magnetic, is the electron shell of the oxygen atom, and this is the electron shell of the hydrogen atom. And so electrons spin fast, so they have relatively big magnetic fields. But in the molecule, they're paired up, and with opposite spins. So imagine each spin pointing in a different direction. And so they're paired up, they cancel out the fields, their fields. and that's true for the atoms of hydrogen and the atom of oxygen. But the nuclei of the particles in the nuclei at the center of the atoms have magnetic fields too. So I've got red for protons and green for neutrons, and there's an equal number of those and an even number of those in the oxygen nucleus. But they pair up too. So one neutron will have an up spin, let's say, and another neutron will have a down spin. And so their fields cancel out at some distance from the nucleus. You don't feel their magnetic fields at all. However, the hydrogen nuclei are spinning balls of charge, protons, and they have a magnetic field that's small compared to that of an electron, but it's real and it's measured. We know exactly what it is. And there are two, and the spins of hydrogen nuclei in molecules of water, in a glass of water, let's say, they are pointed randomly. They can point in any direction. They're just kind of loose. They don't affect each other, and nearby things don't affect them. So they're just loose and point in every direction. So you don't think of water as being a magnetic material. But a water molecule can be slightly magnetic if you line up the protons in a given direction so that they're both pointing in the same direction. So the fields of a water molecule don't have to cancel out, but they normally do. All right. Now, what does water have to do with planets? Well, God formed the earth from created water. And here's a very important verse, 2 Peter chapter 3, verse 5. It says in the Greek and in most modern translations, the earth was formed out of water and by means of water. And that word formed means actually to put together, to place together, to hold together, to compact, to press together. So I think our solid earth was formed from the pieces of water from different nuclei and different parts of nuclei, pieced together, put together. That's what that Greek word means. It's a very interesting word, but it was formed out of water and by means of water. So here I've got a picture of the Earth cross section, and each one of the hydrogen nuclei is all pointing up. Each one is pointing up. And that makes a magnetic field. So the question is, how much magnetic field does it make? Well, I'm assuming that God conserved mass and energy like he does now. And so the mass of the water then is equal to the mass of the water now. Now, if all the hydrogen nuclei are lined up, oh, by the way, if we know the mass, we know how many molecules of water it was back then. And it's 1 with 50 zeros after it, 10 to the 50th power. That's a lot of molecules. And so all of those nuclei are aligned, then you get a fairly substantial magnetic field. And the number you get is 7.9 Gauss. I could put in some more decimal places to mention it, but it's an exact number. We can get it with no doubt. And so 7.9 Gauss at the poles of this ball of water, magnetic poles, is about 13 times the Earth's magnetic field today at the poles. It's about 6/10 of a Gauss. but the hydrogen nuclei can't stay lined up for more than a few seconds. What happens to the field after that? Molecules of water collide, they disorient spins, and start an electric current in the water. And I'm going to show that. Within seconds, this happens. So there's the electric current going westward in the water. And the amount of the electric current, we can also calculate easily, was 250 billion amperes. Now today, the Earth's magnetic field comes from an electric current in the core of 6 billion amperes. So this is quite a bit more. But the bottom line is that the magnetic field would be preserved. Now, we're going to take away the water. What happens then? Because God, on the third day of creation, as I mentioned in my other talk, transformed water to solid earth. And transforming to a solid earth also preserves the magnetic field. So again, we have an electric current in the core of the earth, only now it's a molten metal core, and it's surrounded by a mantle of rock, and it's the earth as we know it today, pretty much. So now the current and the field are preserved by the standard, ordinary, run-of-the-mill laws of electricity and magnetism that God made. And I'm assuming that those were in effect at this point in creation also. So the core is a good conductor. It's a molten metal, like I said, but it does have some electrical resistance. So you're running that current through some electrical resistance. But the total field stays the same. But what happens to the electric current after this? The current runs down like a flywheel. Just like think of the electrons in the core of the Earth spinning around the Earth's magnetic axis like a flywheel. And just like a flywheel gets slowed down by friction, so electric resistance restricts, cuts down, reduces the current. So I'm going to show a little graph here. And the axes of the graph, if you can see my cursor, I've got time along the bottom. 0 would be creation. This is time in years. And from the Hebrew text of the Old Testament, putting together the chronologies, we would have 6,000 years to today. The vertical axis there is the electric current. So this is what simple physics theory says the rundown should look like if there's nothing that happens to mess it up. So take a look at the graph. It starts from 250 billion amperes at the top and runs down to the 6 billion amperes of today. And the simple physics theory says that it should have a half-life of 1,100 years, roughly. So half-life is the time it takes for the current to decrease to half its starting value. So we would have 5.5 half-lives in 6,000 years. And with that, we would get the 250 billion amperes down to 6 billion amperes. So now, this is also simple physics. The half-life that I talked about up here, 1,100 years, in any planet depends on the electrical conductivity of its core and the square of the radius of the core. And there's some other constants in there, but I'm not going to show those. So, but the bottom line is that the bigger the core, the longer the half-life. So bigger planets have longer half-lives for their magnetic fields. And it goes up as the radius squared. So that means big planets have a whole lot longer half-lives than small planets. So now, this was theory. What actually happened to the Earth's current and the magnetic field was more complicated than this. There was a catastrophe that happened to the Earth's core and the rest of the Earth at the time of the Genesis flood. Say about here where my cursor is. And the Earth's magnetic field actually reversed itself, and then it bounced up and down, and finally, about 1,000 years ago, according to archaeomagnetic measurements, it settled down to a steady decay again. So we know what the Earth's magnetic field did. Archaeomagnetic measurements, that's magnetism of pottery and the bricks in kilns and other things like that that get heated, and they lock in information about the Earth's magnetic field at the time. So we know this decay resumed and has been steady for the last 1,000 years. Now, this is all of this the curve I've shown, and all this is theory. But we have measurements of the decrease of the Earth's magnetic field. And the bottom line of the graph is that Earth's magnetic field is fading fast. So let me walk you through this graph too. We have the year 1900 to the year 2010 along the bottom. And we have what's called the dipole magnetic moment. And don't pay attention to the units right now. The magnetic moment is the strength of the source of the magnetic field of the Earth. Now, each of these dots is a measurement that was made, and they were particularly made by an association called the Association of Geomagnetism and Aeronomy, or the IAGA. And they got very accurate numbers from the year 1970 on to today. Every 5 years, they come out with the new number for the Earth's magnetic field strength. And then they extended their measurements, or their method of analysis, and used the same method of analysis on data that went all the way back to the beginning of the 20th century. So, and the error in their data is small. The error bars are smaller than the black dots. So this is a really accurate set of data. And I didn't really look at this data until about the year 2000, and then I found it was very accurate. You notice a little wiggle in the line, a smooth sinusoidal wiggle, they call it. And that comes, I think, from the twisting of the Earth's core back and forth in the east-west direction. And it matches change in the length of the Earth's day. The period is about the same, about 60 or so years for the wiggle and the timing of the Earth's rotation. So, but if you subtract out the wiggle, then you get a straight line on this graph, the red line. And the half-life that this represents, because on a larger scale, it's not straight, but curves downward, or curves upward, I should say, like that graph I showed in the previous slide. So the half-life today is 1117, give or take 7 years. So we know that this field is fading fast, and it's fading at about the right rate. So for the materials of the Earth's core and the size of the Earth's core, we can calculate the rate. and it matches this rate nicely. So the smooth wiggle, by the way, I just want to give credit to one of Dr. Thomas Barnes' students named Clifford Paiva. He called me back in the early 80s, and we discussed the Earth's magnetic field because Dr. Barnes was a pioneer in the study of the Earth's magnetic field among creationists, and his student was interested in it too. And he proposed that there looked to him like there was this kind of wiggle in the data. But at that time, the data was smeared out by different methods of analyses, and it was a lot harder to see that wiggle. So I wasn't sure the wiggle was there, but turns out he was right. So anyhow, we get this nice steady decay plus a wiggle. And what about the other planets now? Well, the same creation theory about the origin of the Earth's magnetic field, I made predictions in 1984, and it was in this article, The Creation of Planetary Magnetic Fields, in the Creation Research Society Quarterly in December 1984. And you can find it online at creationresearch.org. The online copy of this has the figures messed up on it, but you can go back in the files to the original print version and see the figures there. Anyhow, I made 5 predictions. First, that the planet Uranus, which hadn't been visited by a space probe at that time, should have a strong magnetic field. And I gave a number for the strength of the source. And Neptune, the next planet out from Uranus, should also have a strong field. And I gave a number, and those 2 numbers were about the same. And then my article also said that Mars's crust should be magnetized because it, according to the theory, had a strong magnetic field at the beginning when the crust, when God was forming the crust of that planet. So rocks, when they cool down in a magnetic field, get magnetized by the field, and they store information. They record information about the strength and the direction of the field. So then, so Mars crust, and then Mercury's field should decay fast. And I knew, I'll tell you why I knew that in a while, should decay fast. And then the 5th prediction was that Mercury's crust should be magnetized, just like Mars crust should be magnetized. Mercury once, according to the theory, had a strong magnetic field, and so its crustal rocks should also be strongly magnetized. So, but I had actual numbers for items 1, 2, and 4. So NASA made a check. They checked my prediction on item 1 in 1986. And Uranus turned out to agree with the predicted field. Now this is a picture of Voyager 2 at the planet Uranus. And it has, if you notice these little dots here, those are auroral dots from its magnetic field. And it had a magnetic field. Now, according to the creation theory, the field should be on the order of 10 to the 24th power, 1 with 24 zeros after it, ampere square meters. And that is a measure of the strength of the field source. You just, if the current is going in a circle in the core, you take what amount of current is flowing around in the circle in amperes and divide it by the area of the circle, or not divide it, multiply it by the area of the circle. So you get ampere square meters. And so the creation theory gave this number on the order of, within a factor of 3 either way, of 10 to the 24th ampere meters squared. So the creation theory was this. Voyager measured 3 times 10 to the 24th. And the other theory, the other side, the dynamo theory prediction, was 100,000 times smaller. I won't go into the reasons for that, but the dynamo theory is the long ages theory that of what would start up the field and maintain it for billions of years. So it's a theory they've had now since, for over 100 years, since 1919 in various forms. They keep working on it. And right now, it is still kind of a hand-waving theory. It doesn't really make any solid predictions and give solid numbers. But they thought the field from Uranus should be very small. So let's go to the next planet out. 1989, Voyager 2 reached Neptune and flew by it and recorded its magnetic field. And Neptune agrees with this predicted field. So again, the creation theory gave you on the order of 10 to the 24th power ampere meter squared. Voyager measured 1.5 times 10 to the 24th, so it's within the bounds of the on the order of. And I first talked about this in an ICR.org 1990 impact article called Beyond Neptune. So you can go to ICR.org and look at their archive of impact articles, 1990. You should find this. However, later I'll show you a book with this information and much else. So that was last century, 1989. Let's move to this century. In 2001, the Mars Global Surveyor surveyed Mars and found that Mars's crust is strongly magnetized. So this is a map of what they found. The Global Surveyor orbited pretty close and took many passes near the surface of Mars and measured the small local fields from the magnetized crust. But Mars doesn't have any big global field, no overall field at all, only these localized fields. So let me walk you through the chart here. This is longitude. I don't know what they decided to label as 0 degrees longitude, and then 180 degrees, 360. And this is latitude. Minus 90 is the poles, the south pole of Mars. 0 is the equator, and 90 plus 90 is the north pole of Mars. And the colors represent the strength of the magnetization in the crust. So red is normal polarity, and blue is reversed polarity, opposite from the normal direction. And there's a certain number of the strength of the magnetization for each one. And you'll notice these stripes here down near the south pole of Mars. It looks like very similar to the magnetic stripes that we have on the Earth's ocean floor, except those generally run north and south. Maybe you've seen pictures of those stripes of magnetization of the ocean floor of the Earth, and they are reversed and normal. But these stripes are about 10 times stronger. So the field of Mars was quite strong at the time these rocks formed and cooled down, probably near the beginning, very beginning, 6,000 years ago. So elsewhere you see all that stripes. So the point is that Mars once had a strong global field. It has none now, but it had a strong global field when these crustal rocks formed and cooled. So that's another prediction that fit. I didn't have a number for this prediction, but I did know a number for the original field of Mars and an estimate for how fast it should decay. So all of this fits nicely. Okay, I'm going to go forward in time another decade to the planet Mercury. And in 2012, the Messenger spacecraft orbited Mercury many times. And before it orbited, it passed by a couple of times. But in about this time, it went into close orbit and swooped low over the northern plains, especially of Mercury. And that was, it found out some interesting things. But it wasn't the first probe to visit Mercury. There was one back in 1974. And it, before 1974, the dynamo theory, you'll notice here, predicted zero field. And why was that? Because Mercury rotates 88 times slower than the Earth. And the dynamo theories depend on rotation of the planet. So they figured there just couldn't, it wasn't enough to make a field for that size core that Mercury had. And so no dynamo theory, no. Dynamo is the British word for electric generator, by the way. So the theory sort of imagines that fluids, conducting fluids in the core and heat make the fluids go in such a way as to generate a magnetic field. So it's very complicated, and they haven't really managed to make it work yet. So anyhow, this space probe named Mariner visited in the year 1974 and 1975 and found that Mercury has a small but still quite significant field that's about 1% of the strength of the Earth's field. So Mercury, that was a lot more than zero. So the dynamo flunked out on that. Then before 2008, the dynamo theory predicted no decay. But I had a theory that says the field of Mercury should have decayed rapidly, and it should have decayed from the initial value that I had for it at creation to the presently measured value. And that would give you about a 5% decay in 33 years, or for 36 years maybe. So that was the creation theory. And Messenger found in 2012 the decay was actually faster. It was about 7.8% decay. So again, the dynamo theory flunked out, and the decay is a little faster than I was expecting from my theory's original starting point and the present point that it had in 74. So I think the core heated up a little, and it's decayed a little faster as time went on. But that's a little knob that my theory could have, but it was within the bounds of my theory. So, and that's quite a fast decay, by the way, in just 33 years, 36 years. So, so then another thing, the dynamo theory before 2012, before the crustal magnetism was measured, said no strong past field. It should have always been about 1% of the Earth. They had a hard time understanding the 1%, but they certainly didn't want it to be a strong field. So no strong past field. But the creation theory in 1984 said there should be a strong past field. So Messenger swooped over the northern plains of Mercury and found strongly magnetized lava flows. The field was at least 10 times stronger in the past when those lava flows flowed than it is now. And interestingly, it was of reverse polarity compared to the present field of Mercury. So Mercury, like the Earth, evidently has reversed its magnetic field a number of times. So anyhow, I'm proud of the creation theory. I suppose I should, I don't want to have a fat head over it. But let's review all of those 1984 predictions. All of them are now verified. And there's the article. Number one, Uranus has a strong field, and we have the right number for it measured. Neptune has a strong field. Again, the right number measured. Mars has a strong crustal magnetization. Mercury's field decays fast, 7% in 33 years. Mercury's crust is magnetized. And so let's look at some other solar system objects that I didn't make a prediction about. The moons of various moons, including Earth's moon, asteroids, and meteorites, also agree they fit nicely into the theory. They weren't my predictions, but they fit nicely after these fields were discovered. So here you see the Galileo space probe, and in the foreground is the probe, and then a little behind it, but still fairly close, is Jupiter's closest in satellite that's big, called Io or Io, and it's volcanic. There's volcanism still going on. I guess Spike Saris will talk about that. I hope you do, Spike. The fact that Io is still active geologically. And then way in the background here, but is this humongous planet, Jupiter. I think it's just a gorgeous object. I guess God likes pretty colors. And so anyhow, Jupiter's moon Ganymede, which is further out than Io, but it's a rocky planet that they didn't expect to find a magnetic field in. It didn't look like it had a core, and I don't know if they think it has a core now or not, but it has a strong magnetic field right now, and the value of the field fits in nicely with what the 1984 theory says. So then Earth's moon once had a strong magnetic field. It has 0 global fields right now. It just, it's totally dead as far as magnetic field is concerned. But it once had a strong magnetic field, according to the rocks that various astronauts brought back and measured their magnetizations. So it had a field at least as strong as Earth's field is now. And that's a real puzzle to the dynamo theorists, because the moon rotates slowly, only once every 30 days, and it has a very small core that can conduct electricity. And the smaller the core, you remember, the shorter the lifetime of the field should be, the half-life of the field. But they just didn't see how it could have ever had a dynamo, and they're still arguing with each other about it. Some say, well, it did have a dynamo, and others say, no, something else made these fields that the rocks measure. But anyhow, it fits the Earth, fits the 1984 theory nicely. Then 2 asteroids were visited by probes, Gaspra and Braille, and they are strongly magnetized. So they had to, when the asteroids formed, they had to be either in a planet or very near a planet when they cooled down below about 500 degrees C, where they would start recording a field. So that's good to know, because way out, far from any planets, the field from those planets is very small. So out in most of the solar system, there isn't much magnetic field. And then meteorites were magnetized also. They were magnetized in about a 20th to 1 Gauss. About a half a Gauss is the Earth's magnetic field. So the meteorites were also formed either in a planet or near a planet when they cool down. So, but anyhow, these fit the field, the predictions nicely. So let's go now to the biggest object in the solar system, the sun. And it agrees with the theory well. Now, astronomers can measure the sun's surface magnetic field by looking at its light spectrum. They can measure it at individual points all across the surface of the sun. So I'm going to show you what the magnetic field looks like every 11 years. It looks like a nice, clean dipole field. That's 2 poles, north and south, every 11 years. But in between those times, the field, not all the fluid of the plasma on this near the surface of the sun rotates westward at the same rate, and at the equator it rotates faster, and that grabs the lines of force, the magnetic lines of force, and starts wrapping them around the sun. So it twists them. So, and the field coming out diminishes. And then as the field gets wrapped around the sun, like the lines of force, like a ball of twine, some of the field pops out of the surface at different points and makes sunspots, where the field sort of loops and twists, and there's so much tension in it that it pops out of the surface of the sun. And so this over here is 5.5 years after the first left-hand side, and this is at sunspot maximum. And by that time, there's very little field coming from the poles. And then the field reverses its direction sometime in there. And then the field starts unwinding, like unwinding the ball of twine. And it goes back to less and less. And then 5.5 years after it started unwinding, it's back to the field like it is here, except that the field is in the opposite direction. So the sun reverses its magnetic field. But every 11 years, the field is nice and clean, and we can analyze it easy. It's not all wrapped around the sun. So at those times, the magnetic field of the sun is about, a little less than what the created field. The last sunspot minimum we had, I believe it was 80% of what my theory says the created magnetic field should be. So that means that all this twisting and churning and rotating and reversing chewed up some field, and we can calculate how many cycles that was in 6,000 years, and that gives us an energy loss of about 0.15% per cycle. So these reversals chew up energy. And I think that happened on the Earth too. During the Genesis flood, we had about 100 reversals of the Earth's magnetic field recorded during the year of the Genesis flood, when all the rock layers were being laid down on the continents, and when the mid-ocean ridge was spreading seafloor out from it and recording those magnetic stripes I mentioned. So anyhow, Sun agrees with the theory nicely. So why am I emphasizing this? Why is it important that we have fulfilled predictions? Well, the answer is that solar system data fit the theory only if you have biblical conditions. First of all, the smaller bodies in the solar system that have had some amount of decay, like the Earth, and smaller, and the Moon, very small, they need a time scale of about 6,000 to 10,000 years. So the larger bodies there's a larger time limit from them because their fields decay with a longer half-life. But so the solar system, though, as a whole, has to be pretty young, or the theory just doesn't work. And then planets and the sun must start as water. Why? Well, the stuff of which the planets are now made, silicon, oxygen, calcium, iron, molten iron. Molten iron isn't magnetic, by the way. Those, if their nuclei were lined up, would generate too little field. Their nuclei aren't very magnetic. And but for the sun, let's say we started off with pure hydrogen, or started off with pure hydrogen for anything, we would get too much field, about 10 times more field than we observe. So the biblical conditions are a young world and a young solar system, and it specifies that all these fields started off as water. Okay, let's see, how much time do I have? 1:22. I guess I have a little bit more. Let's zip through.
Keep going.
Okay, stars all have magnetic fields. Earth's field is about 1 Gauss. Ordinary stars, including our sun, about 10 Gauss. Magnetic stars, about 1,000 Gauss. White dwarfs, 10 million Gauss. Pulsars, 1 trillion Gauss. And the thing called magnetars has about the largest measured magnetic field we see in the universe, 100 trillion Gauss, 100 trillion times the strength of the Earth's field. That is a whopping field. But all of these can fit the prediction, the creation theory. Now, what about the biggest objects in the universe? Galaxies. It turns out that galaxies have magnetic fields too. And the field is 1 to 10 millionths of a Gauss. 1 Gauss is, or half a Gauss is the Earth's field, for example, for calibration. And if you can see little short lines all along here, those represent the strength and direction of magnetic field all around the Whirlpool galaxy. I think that's right, Spike. Maybe you're going to talk about the Whirlpool galaxy, but looks like most spiral galaxies have a magnetic field, and the lines of the field follow the spiral arms, which is something very interesting about, has some implications for various theories about galaxies. So this can fit the creation theory, but I think another process may have been involved in addition to the original field from the water. So the cosmos itself may have a magnetic field, but it would be very weak because all that magnetic field in the original ball of water I mentioned in the other talk would have been stretched out and scattered out over 20 billion light years radius, and that would weaken the field. And so it would be quite small, but at any rate, it's too small for measurements. So here's where you can find out more. This 2016 book, Earth's Mysterious Magnetism. Let's see if you can see it here. And that of other celestial orbs, and by me and a good friend, Mark Despain, who's an engineer, electrical engineer, and he's a good writer too. And he wrote this very readable book. There are no equations in it. I think even if you didn't have science in your background, but only liberal arts, it's sort of at least it's at the level a liberal arts major in college should be able to understand with a little bit of work. Or let's say you are bioscience, if you weren't a physical science major, but you can still, it's still easy. I shouldn't say easy. It takes some dedication to read it, to understand all in it, but there's a lot in it. And the book is available at creationresearch.org, their bookstore, creation.com, their bookstore, or amazon.com as an ebook. And creationresearch.org has 3 different types of ebooks as well as the hard copy. Okay, I'm winding up now, down to the finish line. Magnetic fields show God's handiwork in the heavens. It can explain the magnetic fields of planets, moons, asteroids, meteorites, the sun, stars, pulsars, magnetars, galaxies, and maybe the cosmos. So I thank you for your attention. Do we have time for a few questions, Gary?
We do have time for a few questions. Are you ready for them?
I am ready.
Great. First of all, thank
Talk it
you.
to me.
Thank you very much. Excellent. Okay. Question. If the moon has no magnetic field, how does it have a gravitational pull?
Ah, you missed the little statement I said at the beginning, which says that magnetic fields have nothing to do with gravity.
Right. Okay, good. In one of the slides, you mentioned 250 billion amperes. How do we know that value?
Amperes, 250 billion amperes.
Yes.
From the same calculation that gave us the 7.9 Gauss, which simply comes from the adding up of all the fields from the little hydrogen nuclei. We get a field, and when that field is produced by an electric current, the answer you get is 250 billion amperes. That's where it came from.
Good. This question relates it to your first talk. You indicated in the first talk the Earth was uniquely created prior to other bodies. You postulated that the water balls left over from that creation eventually turned into stars and planets.
Yes.
Now you're indicating the way that the Earth was created is similar to the way other planets are created, magnetic field creation. So how do you reconcile those two things?
Well,
Shouldn't there should be vast differences between the Earth and other planets, this questioner thinks.
oh, let me see. In that talk, and also in this one, I pointed to a verse that said the Earth was formed out of water. And so the other talk told how all the other bodies would be formed out of water according to my theory. So I theorized that that as the waters above the heavens moved out above the earth, they left behind balls of water, which then God turned to stars, probably on the 4th day. So both the earth and the stars started as water. And if they all started as water, then I've got a nice theory for their magnetic fields.
Right.
Hope that's clearer.
Yep. question, is there a purpose to magnetic fields in stars and galaxies, or are they just byproducts? Not that I think God has any byproducts.
Well, I think the main purpose was to show God was leaving us some fingerprints to show how and when he created. Now, Gary, I'm afraid I've got to disagree with one of your points. Okay, I'm sorry. Maybe I don't need to say this, but it's in my book, in the foreword of the book. It's a piece of creationist urban legend that the magnetic field is necessary for life on Earth, and that it protects us from cosmic rays. But our main protection from cosmic rays
Yes.
and the solar wind and the particles is the Earth's atmosphere.
Yes.
And the magnetic field of the Earth actually doesn't shield us so much from the solar wind and cosmic ray particles as it does to scoop up those particles and make them circulate around the lines of force, and then it dumps them down on the polar latitudes. Mm-hmm. So that radiation that was arriving near the equator is now arriving at the pole, and it's not dangerous to the Eskimos, people who live in the lower that area. They don't suffer radiation burns or any particular amount of radiation, and the reason is that most of the cosmic rays get stopped above the Eskimos' heads in the atmosphere, and they make the beautiful polar aurora phenomenon. Yeah. So about the only people that would miss a magnet. Oh, there's another thing. The solar wind does blow away a little bit of the Earth's atmosphere every year, but it wouldn't blow away significant amounts of the Earth's atmosphere until you have millions of years elapsing. So the evolutionists say that we wouldn't have an atmosphere if we didn't have a magnetic field, but they're assuming that the Earth is millions of years old. If it's only thousands of years old, that process doesn't matter. Right. So we qualify it. It depends on how long you think the Earth's been here. Right. So anyhow, the only creatures that would really miss the magnetic field if it went away today would be certain birds and bacteria that use the field to navigate by. But I imagine they would find other ways to navigate. So
yeah, good point.
Yeah. So I'm sorry, nope. Gary, but
you are were absolutely correct.
And yes. Dr. Tom Barnes helped propagate this error. So he was. Mm-hmm. So yeah. Anyhow, sorry about that.
No, that's good. I did misspeak. You're right. Okay, I'll deflect myself right now. So another question, just what caused the magnetic field reversals during the flood?
Okay, I have a whole chapter in my book about that with graphs. It's quite a complicated process, but there were several things that happened to the Earth's core to cause rapid flows, up and down flows of the fluid in the Earth's core, and that is a electrically conducting fluid. It's molten metal, and that carries lines of force with it. And this action the result of the action would be to eventually push up lines of force through the fluid and out into the Earth's mantle, the rocky mantle, and where the original lines of force would die away. But the pushing of the lines of force through the fluid generates an electric current in the opposite direction and a magnetic field that's in the opposite direction as the original one. And that field gets bigger and it emerges above the core and out into space. So this process would continually reverse the magnetic field. So that's a theory that I made, and I vetted it at the, let's see, it was the 1990 International Conference on Creationism. So you can go to their website and look up their proceedings in 1990, volume 2, I believe, and you'll find that theory for reversals. But it's also in the book. So one chapter in the book talks all about that.
Great. New Horizons visited Pluto in 2015. Did that mission collect any data pertaining to your theory and predictions?
No, unfortunately, they decided that since Pluto was mostly a ball of ice, it couldn't have a dynamo, so it shouldn't have a magnetic field. So they decided they weren't going to burden their spacecraft with a magnetometer. And I'm sorry about that, because they might have found the field. But I didn't actually think that Pluto would have a field in my 1984 paper, because it does seem to be mostly ice, and it didn't look like it would have a strongly conducting core, which meant that whatever field it had to begin with would have long since died away, like the moon's field has. So we maybe didn't miss much.
Okay, sorry, last question. There are a few other ones, but what is the secular response to your theory?
Mostly silence. Maybe Spike knows a bit more about that, but I've observed some interesting things about their publications in recent years about the magnetic fields of these planets that the probe measured. And I kind of get the feeling that they know about it, but they just don't want to say anything about it, especially, since they're more often wrong than I am. So.
Exactly. Very good. Thank you very much, Russ. I
Thank you.
appreciate it. You bet.